welcome to our presentation concerning our DNA projects here at Aachen University. Before we go into the details, I want to show you a short overview. So in total, we have 4 accepted DNA projects for Aachen University right now, and we have 2 of them which are successfully finished at the moment. One DNA project deals with information evolution and design, DNA ID 17. One DNA project with the name Lines of Descent, coming from the material science area, DNA ID 72. We have one project which is currently work in progress, which deals with, generally speaking, the visualization of sun-grain kinematics in an unsteady data set. And we have one project which is still pending, and we are waiting for the visitors to contact us for further steps. And now we want to go with regard to these 3 projects which we have finished or which is in progress more into detail. And first I want to hand over to my colleague Andreas Hamacher, and he will present you some more insights for the first 2 projects which are already finished.
Yeah, 2 DNA projects I want to inform you about. The first one is called Information Evolution in Design, and it's about visualization and analysis of the evolution of large-scale complex information networks. I will talk a bit further about that. It's quite hard to understand from only that one sentence. And in these large-scale networks, the research collaborators from the University of Zagreb also wanted to make performance analysis on the hardware we had here in Aachen, mainly on the evaluation of parallel CPU and GPU or versus GPU implementations of 3-dimensional force-based graph layout algorithms. You can see that later in the picture. And the third point I will also regard a little bit more later. After the visit, the research focus of that project collaborator switched a lot to the human capabilities of understanding these large-scale networks in a virtual environment. So what our collaborators started with is roughly explained in this slide. This is a picture of them which they used for a publication. And you see the graph-like structure, and basically said each bubble is kind of, they called it information item. And they had or generated these graphs for various set of field of application. One of them was like a ticket tool for car design, and they made a graph out of how the design of that car evaluated over time. A second application of such a graph was the switch or the evolution of keywords in publications for certain journals. So it is a very generalized idea. You have a graph, each node stands for some graph item, some piece of information, and the interesting thing for them was how the nodes and the graph itself evolved over time. Where were new clusters generated, which clusters died out, and after the task of only visualizing it, they did what is quite seldom done in visualization. They started to try to evaluate the benefit for their research community, which is mainly engineering. And I don't know how far they are yet with their evaluation of the benefits, but they got a great step further on that. We had a visit from our collaborators in November last year from the University of Zagreb. 3 people visited us. The head of the visit was Dr. Mario Storga from the Mechanical Engineering Institute, and also Dr. Tino Stankovic. He switched in the meantime to Zurich, and they had 1 master student with them of the implementation part. The picture you see right now is, yeah, it's hardly capable of describing the whole scene. It was, this is only a screenshot of the software they wrote, and they were able to run that software, or I should first explain the picture. What you see here is that large graph-based network with a force-based layouting algorithm and also with a clustering algorithm applied. And they had networks with 200,000 to 2 million nodes, roughly. And they evaluated this piece of software in several terms, which I said at first. One was the performance capability here at Aachen, because we had a better suited computer cluster to do this performance analysis. And also we were able to run this kind of software in our cave, where these researchers for the first time experienced an immersive visualization. And that was also the first time that we here in Aachen were really seeing clustering applied on graphs in an immersive environment. And after quite a short time, the talk, the evaluation with the researchers switched to in what extent are humans capable of understanding such large graphs, and also the changes in such large graphs in virtual environments. I don't know what the status is right now, but the guys from Zagreb contacted colleagues of them which are mainly involved in psychological studies, and maybe they wanted a follow-up project about human capabilities of understanding such large networks.
Are you able to explain the content of this graph like this? What does it mean?
This graph was about a car design conference from the years 2004 to 2009, and the clustering here is about certain keywords in these submissions to the conferences. It's hard to see the actual data of the graph right now. You don't have any keywords attached to these graphs, or you don't have any labeling of the clusters in this screenshot. The reason for this is since the researchers before were looking at the graphs on a very small scale. I switched 2 pictures before, or 1 picture before. Here you are really on a node and edge level, and you can annotate the edges very accurately. But it's a really small graph. How many items do you have here? About 15. And in this here, you have tens of thousands of nodes, which mostly you can see, and only the annotation of the clusters, which are separated by the colors, would be beneficial. And from the implementation point, we didn't get that far in the time.
What kind of annotation do you put on the graph in order to have the yellow color, the blue color, the green color, and so on, in order to to find this kind of graph and to make this color, which should have some semantics, I guess. What is the association of a color here, and which is the kind of summary you make with this kind of colors?
The color itself doesn't have any meaning except that each cluster has its own color. And in an immersive environment, you see that these clusters are very good separated in the dimensions, but that's harder to see in a two-dimensional picture. But it is possible to annotate all the clusters like with their main keyword. Also, the force-based layouting was based on the main keywords, and it would be possible to annotate these clusters. But as I said, it was just a problem of time to attach these annotations. And then, if we would have had more time, it would also have been beneficial to do a selection of a certain cluster and then go to do a deeper analysis in that cluster, to concentrate on one cluster and to also go into a smaller level of detail to again look at the connections between the nodes, which is not possible here.
And what was the navigation capacity? Is it in 3D? I guess it is in 3D. Did you use the perception in 3D? Was it meaningful? Or?
Yeah, that was more or less the main outcome of the project. So it is completely in 3D stereo application. It runs on our cave here in Aachen, which is a display system with 24 displays. The application runs on 48 instances. And yeah, we had a full immersion of the user of Professor Storger in that graph. And we talked at the end of the project a lot about how humans are capable of understanding such a large graph network when augmented in a virtual environment. And I don't know what the current status is, but he wanted to talk to some psychological guys to evaluate further that question. The title of the second project I want to present is called Lines of Descent, and let's say it takes place in thermodynamical simulations. And I have to state at first that it was really hard for me to get the whole idea of the simulation chain in that project, and therefore I'm not really capable of explaining the model building in that project. So they did a numerical or computer-generated simulation of a thermodynamical phenomena about multi-component melts. So maybe you know a bit about thermodynamics. It's every time about how the pressure changes, and with the pressure the temperature changes, and then the different components go into different phases like liquid or crystalline or something like that. And they did numerical simulations on a lot of components and are very good at that field. They are more or less the first ones in Europe who try to tackle such a very complex system in that case of material science and earth science. After the numerical simulation, where I can't talk about too much because I really don't understand it completely, they try to separate phase fields inside their numerical phase. So they want to compute how big is, let's say, the crystalline phase of this and that element in their multi-component melt. And therefore they at first try to locate and also evaluate how large a so-called equipotential zone of that specific melt is. I go to a picture. On the right side, let's say you have the purple phase on the right, or the red to purple phase. this is one phase inside a multi-component melt, and they needed to evaluate the size, but also the borders of that phase. What's very important to understand, and also hard to understand, is that it's a high-dimensional problem, and they are using convex hull techniques, which beforehand shrink their dimensions to a three-dimensional problem. And therefore we are only capable of visualizing the multi-component melt as a tetrahedron, which is then 3D, and also computer graphics algorithms are part of the numerical chain to do some evaluations on that multi-component melt. So after somehow understanding the simulation and the computer graphics algorithms that are necessary to evaluate some part of that problem, we focused on the visualization part of that complete problem, because there we saw the most opportunities to aid the researchers involved in that project. And what we did afterwards is a visualization of coherent forms in the phase fields that should aid the researchers towards more extensive experimental investigation or to more detailed and satisfactory thermodynamically parameterization. So basically, to be able to make a visualization that is more or less in their comfort zone, which they are used to have. So our research partner was mainly Professor Giulio Ottonello from the chair of geochemistry from Genova, and he visited us quite recently, so in the last month. And what we did during that visit was the evaluation of a test case he gave us, which is the picture I will show later. And we aided him by just extracting iso volumes and iso surfaces for the phases, and then talked a bit more about the generation of the lines of descent, which is the title of the project. And yeah, he first came to us with the left picture that quite roughly approximation of the phase field, where there was no separation of the different phases, and where the connection. So what you see is a tetrahedron mesh, and each visible mesh point is a contact point of two phases. So in the right picture you see the different phases, differently colored, and in the left picture you only see the contact points of these phases. And yeah, what we did is we separated the phases, we gave them each a color, and started naming them and started giving them tools to interactively separate them, visualize them. It was, to be honest, a very basic interaction we gave them, but as you can see from the difference of the pictures, it was quite a benefit to them, and was only achieved in only 4 days.
How many time did you pass for development of this specific application? It's a question I just think about for the overall points in about TNAs. Usually it's not only coming on the platform, but you have to adapt your software, the interaction techniques, the way to get information from the guests and so on. How many time did you expect on this project in order to complete the a priori development of this use case?
That depends a bit. So at the end of the project, we discussed very extensively in what could be done in a follow-up for the project. We showed them a lot of techniques on other data sets which could be beneficial to tackle their problem. And what we agreed upon is that they met themselves internally and talk about what of these methods could be beneficial, and then they wanted to talk back to us on maybe what to implement. And I can imagine that there will be a kind of follow-up project to that, which will start with a selection of the method catalog we gave them, and that we start trying to aid them, to help them to use that methods. I cannot make any kind of how long it will take, because I don't know what they will at the end want from us.
For this, which was already done, it was 1 week, 2 weeks of work or more?
Yeah, 2 weeks of work, yeah. And most of the time, to be honest, went in understanding their problem.
Give you a short overview of our ongoing work with the DNA called visualization of 4D discrete data, sand grain kinematics under loading. The project partners in this project are from G-Scope in Grenoble, Frédéric Noël and Patrick Negro. From Laboratoire Y3S5 Grenoble, Zino Viciani and Edward Ando. And from our side at the VR group at RWTH Aachen University, it's Sascha Gebhardt and myself, Stefan Selzer. The whole thing is work in progress. There are no results yet. Give you some short overview of what is planned. During this work, there were some phenomena discovered, and which arise some open questions, and we hopefully will aid him in this program at our side at the RWTH Aachen with understanding the problems and the phenomena by setting up a visualization in our virtual environment and setting up an interactive interface to explore and analyze this data that they produced and hopefully help understand and explore and analyze the problems there.
Did you develop the model for the particle simulation? Because from what I know, the particle simulation is a very tricky task. Or did you use an already existing model, some library?
But what has been done by the Y3S laboratory is an experiment on grains. So it is not a simulation. It is a real pressure on a sample of grains. There is something like 85,000 grains which are in the sample. And this sample of grain has been analyzed and observed through tomography technology. And through image analysis, the Y3S laboratory recreated all the grains and all the shapes of the grains and is able, step after step, over 15 steps, the position of the grains, and they are able to follow the grain from one step to another step. Now what we are doing with Y3S is the selections of the navigation tools and the interaction system that we can provide in order to navigate in this sample in 3D, in order to observe what happens in 3D and to create new behavior laws of granular media, which is not a simple point, because usually you just put cutted planes in order to understand what happens. And here, maybe we will see in 3D more behaviors and more complex behaviors that cannot be observed easily with usual display. So that's the main topic, and there is no simulation, just observation of experimental data set.
You are planning the data from these experiments to improve the simulation in the future?
Yeah, sure. But what they expect to do is to refine the behavior laws about the granular media, and to be sure that they could explain when there is a cutting plane, which is a 45 degrees plane respect to the pressure session, usually 45 degrees, to explain why this 45 degrees and what are the, where it could be in the beam. It can be more or less high in the beam. So to be able to anticipate these things thanks to a behavior law. But it's not clearly identified. There are some laws, but they could improve these laws thanks to this analysis.